Okay, we can see your screen. Nice white background in the Sheffield system.
I guess I just made the same mistake John made. So I guess because I have some audio to share, so I guess I will share them to just turn on the share sound option.
Okay, in your own time, please start.
Thank you. Hi, everyone. So I'm Zehai too, and I will be presenting the Sheffield system for the second Clarity Enhancement Challenge. And this work is conducted with also Jisi, Ning, and Zhang. So first of all, I would like to give a quick recap of CAC2 scenarios. The figure in the right, Zhang just showed as well, is an example scene in CAC2. As you can see, there's target talker delivering the target speech to noise sources and a listener. So all of these are simulated in a domestic environment. Also, there are some key points that differ from CAC2, CAC2 from CAC1. So the first thing is that the listener head rotation is simulated, which makes the scene a little bit more dynamic than CAC1. And there are 2 to 3 interferers for each scene, and there are more varied interferers. Apart from the speech and domestic noise interfering, the music interferers are also included in some CAC2 scenes. Also, the SNR range is from -12 to 6 dB now, which makes CAC2 much more challenging than CAC1, I guess. Also, for each target speech, a number of speaker adapt speech are provided, which can be used to extract the target speak features to help better enhancement. So essentially, the CAC2 scenes can be described as the figure shows. So a target speech is firstly degraded by some external degradation, which are interference that can be speech, domestic noise, or music, and their combination as well with also the room reverberation. So the aim is to build such a hearing aid enhancement system that after the noisy speech goes into the ears of hearing impaired listeners and suffers from the internal degradation caused by hearing losses, the intelligibility can be improved. So to tackle the external degradation and bring compensation for hearing losses, our hearing aid enhancement system consists of a noise module and with also an amplification module. So here is the overview of our system. It is optimized basically in 2 stages. In the first stage, neural network noise suppression model is trained, and it takes basically the noisy speech and the speaker adaptation speech as input to perform multi-channel target speech extraction. And in the second stage, FIR filter-based module is to optimize to perform the linear amplification for hearing loss compensation. So this module is optimized with an approximately differentiable half-speed, which is the object evaluation metric in CAC2. So here, so the noisy module is DN based, and the convolutional kernels and the layer normalization within DN are kind of made causal to introduce no extra look ahead so that it can meet the latency requirements. And DN is trained with the complex spectral mapping loss, which is in time frequency domain, and consists of the L1 reconstruction of real, imaginary, and magnitude, basically. So here is the simple structure of the noise suppression. neural network. So in order to extract the target speech, speaker embedding network consisting of a bunch of conformity blocks are used to extract the target speaker embedding from the speaker adaptation speech. And the speaker embedding is then multiplied with the conformity block processed noisy speech and fed into the following target speech extraction dense unit. So as for the amplification module, of course, it needs to be able to be customized towards different audiograms. And we use a simple neural network to do that. Also, as I mentioned previously, we implemented a differentiable approximation to Husky so that it can be used as the optimization objective. Also, a loudness constraint is added in the optimization objective to prevent over amplification so that the enhanced speech is not too loud. So here is the structure of the amplification module. And a DN of a very simple DN of 5 feedforward layers takes the audiogram as input and outputs the gains at various frequencies to generate a corresponding FIR filter, which is then applied to the denoised speech processed by the dense unit and to provide linear amplification, basically. So here is an overview of how Husky works. So basically, the process, the enhanced noisy speech and the corresponding reference clean speech are firstly processed by the hearing loss auditory model and the normal hearing auditory model, respectively. And their envelopes are then used for feature extraction, and the extracted features are then used to compute the correlations. And then the correlations are compressed to extract 10 correlation features. And at the last, an ensemble of neural networks are used to map the correlation features to Husky scores. So in order to use Husky as the optimization objective, some approximations are done in the auditory model and feature extraction stage, such as let's say replacing the recursive IR filters with some FIR interpretations so that it can be so the computation can be done in parallel. And also we did not use the voice activity detection mechanism in the feature extraction stage. And we also retrain at the end to replace the network ensemble in Husky. So the retrained DN takes the approximated features as the input and map them to the ground truth Husky scores. So as the and also the loudness constraint is applied to the envelopes. That is kind of punishment if the processed or the enhanced envelope level is higher than the reference one. So here is the experimental setup, basically. So the baseline is the neo amplification plus a simple compressor, and the evaluation metric we show in this presentation is basically the better ear Husky. And the data we use is basically the 6,000 provided training signals, and we use the 6-channel mixed signals as the inputs and the 2-channel target signals as the training targets, which are echoic, and I think that's a little bit problematic. Also, for our system, we were operating this system at 32 kilohertz, and because we made everything causal, so the latency is basically 4 milliseconds, as the SDFT window length is 128. So here are some objective evaluation results on the development set. The MC conf testnet is our CAC1 system that performed pretty well in both objective and subjective evaluation in CAC1. However, it provides only limited improvement over the NLR baseline, which kind of shows the difficulty of CAC2. And the target speech extraction dense unit can make further improvement with the target speaker information. And the optimized amplification helps the final Battle heart speed score reaching slightly above 0.5. So here we plot the development set Battle heart speed scores along the seeing SNRs of unprocessed signals and NLR amplified signals and the enhanced signals by our proposed system. It shows that the significant improvement can be observed in high SNR range, but for low SNR signals, only a relatively small portion of signals can get significant improvement. So here I also got put 3 pairs of unprocessed signals and their denoised signals at relatively high, mid, and low SNR scenes. And I guess I can play them here. So you might want to turn down your volume a bit so that it's not too loud. So basically this, the first one is the kind of high SNR signal.
This is not difficult, even for an inexperienced cook.
And this is the denoised one.
This is not difficult, even for an inexperienced cook.
I think for the high SNR signal is quite intelligible, although it's quite noisy as well. And this is the kind of mid SNR scene.
Shall we proceed and wait for revelation?
And this is the denoised one.
Shall we proceed and wait for revelation?
And here comes the very low SNR scene. And for me, I can basically hear nothing. And here's the denoised one. So basically, as we can tell, for the kind of mid SNR scene, the denoising kind of works, but it brings also a lot of distortion. And for the very low SNR scene, it's not only just the distortion, but also the I think there's plenty over kind of suppression as well. So we also did some additional analysis. Here we show the heart speed differences between 2 and 3 interferers at similar SNRs. If you look at the figure on the right, you can observe that the at similar SNRs, speech with 2 interferers are slightly more intelligible than those with 3 interferers. And the difference is clearer for the enhanced signals, although it is kind of less significant from -5 to -1, I would say, to 1 dB probably. And here we also show the Battle heart speed distribution of the scenes with speech interferers, with music interferers, and with only noise interferers. So in most scenes with the music interferers are comparatively least intelligible. And for high SNR scenes above 0 dB, it is actually quite clear that those with only noise interferers are much more intelligible, which is actually not that surprising. However, the gap of the enhanced signals are kind of not that big, because presumably the enhancement system did okay job, but for the low SNR scenes, the gap among these three types are very small for the unprocessed and narrow amplified signals. So I guess it's because the signals are not that intelligible anyway. So the kind of interfering types does not matter much.
Zehai, you've got 90 seconds left.
Right, I'm coming to the conclusions. So basically, the overall improvement, the overall objective improvement of our process system can bring the better high speed from 0.16 to 0.5. Also, we can tell that the DNN noise suppression does not significantly improve intelligibility for especially low SNR scenes. And at similar SNR levels, since with more interference sources and music interferers are less intelligible. And I guess here is some points I think we can do for the listener adjustment in the future, probably. And because currently the amplification provided is solely based on the audiograms, and probably in the future, I think we could do something like a signal-aware amplification. And also, I guess, because nonlinear compression is a very important thing for hearing aids, and currently we're doing just the linear amplification. So probably in the future, we could provide some optimizable nonlinear compression. And that's it. Thank you for your attention.
Thank you, Zehai. Thank you very much for an interesting talk. We've had a couple of questions asked in the question and answer. Someone asked what the FFT length was, and Trevor's replied it was 128 points. And then Bijit,
yes.
And Bijit has asked, are you not using beamforming?
Not really, because to be honest, it's a pretty late commitment for us to participate in the CEC2, so we didn't really try many combinations. So we basically just kind of replicate what we did in CEC1 and use the solely DNN module to do the noise suppression.
Okay, thank you. We'll give it a couple more minutes for any questions to come in from the floor. While I wait for those, I'll ask one myself. What did you find particularly challenging about CEC2? What was the hardest bit?
I think for me is the low SNR signals. So as we listen to some demo signals, it is really challenging to extract the speech from these quite noisy scenes. I guess that's a major challenge, I would say.
What were you most proud of solving?
Sorry?
What were you most proud of in solving?
That's a difficult question. I guess the system we propose can kind of bring improvements in high SNR signals, and we also did some kind of engineering work as well to implement the differentiable high speed and to make it to optimize our system. So it's something it's something that we achieved.
Okay, and I've also got one technical question. You mentioned you were using complex spectral mapping.
Right.
I've not heard of that before. What actually is it?
So basically, in our CEC1 system, we use the SNR loss to kind of to optimize the DNN. So it's basically to try to encourage the neural network to generate to get the loss of SNR as high as possible, and this complex spectral mapping loss is actually operating in the kind of frequency domain. So firstly, we got the signals turned into the spectrograms. We got the noisy and the clean kind of spectrograms, and these laws actually compute the L1 reconstruction of the spectrogram of the kind of real part and imaginary part, and with also the magnitude as well. So basically it operates in the time frequency domain.
Okay, thank you very much. I can't see any more questions, so thank you, Zehai.